Okay, so I just want to talk to you about the Cosmos Statistics Initiative Residence Program number 5. So I was in Python and Astronomy number 1 in the Netherlands, and I talked about the first CRP, Coin Residence Program that we had at this point. And I have to announce that now we are on number 5. So this is indoor, it's a residence program in the sense that it happens in a house. I have many people ask me what is the topic of the meeting. There is no topic of the meeting. The only thing is that for applying, you would be willing to collaborate with astronomers, computer sciences, and statisticians, and a bunch of people working in the industry. They all have different backgrounds, they all have different levels and seniority, and they all talk different languages. I mean, Python, R, statistics, and whatever, and you have to be open to collaborate with these people. So if you are willing to try to get this, once we get the list of the people who applied, then I will send to all of, we send to all of the successful applicants. This is people we have this year, and these are their expertise, and the participants themselves will propose projects, right? And the projects will be chosen based on the expertise that we have that year, and everybody votes, and we decide the projects as well. The venue is in a house. It's not a conference. There is no talks. There's no lectures. There is no schedule. There's no poster. There's nothing. There's no boards in the house. And in the end of it's 7 days. In the end of the week, we are supposed to have a draft of the paper. This is the 5th time we do this. We have 11 papers at this point. So our productivity is in more or less 2 papers per week of work. Obviously, in the end of the week, a draft, I mean the hard coding part, the argument, and a very rough draft. Obviously, writing takes time. And so how long after the meeting the paper will be published depends on how long people will keep writing after the meeting, okay? And just something else that I have to tell you, we do not have the organizers does not hold the power to decide the participant list. If you coming to the meeting and drinking coffee all day does not guarantee you authorship. Okay, the first author will be the guy who keeps writing to the end. That's the first author. Okay. Sorry. Yes. Yes, the person who keeps writing to the end will be the first author, and the order of the other authors will be decided by the first author at the end after the paper is ready. And if you want to argue with the first author about the order of the authorship, it's okay, but it's between you and them, you and him and or her, and we don't have anything to do with that. This year we are going to Greece, so this is the first reason maybe you would like to come. It's in September. Normally we stay in the last week of August, but this year because of the IAU meeting, we are going to be in September. As I said, it's 7 days. The paper, I just want to make sure that the paper is not, this is not a paper writing workshop, right? This is a community building workshop. What we want is for you to be in the house with other people working in something you like and breaking jargon and community barriers all day. And in the end, we have a paper because the system required that of us and because that's what we do when we are in a room with people who likes to work on things together. The papers are only a natural consequence of the environment. It's not the main purpose of why we are doing this. But it's a very nice output. So if you go to the webpage, there's also a link for the Coin Toolbox. And in the Coin Toolbox, you can see all of the projects beyond the 11 papers. We also have web apps, things in R and Python, because you have a statistician, so you also have to talk to them. We also have projects in R as well. And also Galaxy catalogs, photometric redshifts catalogs in order to guess the representativeness of between training and test sample for photometric redshifts. And just please take a look. And if you want to talk about the meeting, you can talk, or we have me, Rafael, say hi, there, which is one of the organizers, and Miguel, who has already been with us, say hi. So we can ask for any of us, if you are interested on this, I'll be very happy to talk to you about it.
Thank you very much. Next we have Sophie, followed by Abby.
Thank you.
So just as a reminder as to who I am, did that work? Perfect. I'm Sophie from Trinity College Dublin. And so this is my Twitter handle. And the stuff I'm going to be talking about is on that website on the top there. So how many people have heard of technology readiness levels, just to gauge the audience? Okay, so if not that many. So you think of it as the way to kind of measure how mature some technology is. So say you're developing software for customers, or you're building an instrument to go on a space mission, the different levels tell you how far along you are. And it's an important topic for space weather community at the moment, because we started operationally forecasting space weather. So just like in weather, if you have a prediction of how likely it's going to rain tomorrow, we predict how likely the sun is going to give off a solar flare tomorrow. And so for operational purposes, these sorts of progressions through different levels of developing a project is really, really important to define. And at the moment, space weather kind of lags behind meteorology in a little bit, in the sense that we don't have international standards. We don't really have very good guidelines in these sorts of areas. So an international forum was set up. It all started last year from a workshop run by NASA CCMC, where we talked about these sorts of problems and how we can take what's already been done in these sorts of things like TRLs and how we can apply them to our space weather community, and hopefully help researchers who want to take their research project and transition it into something that actual operational users can do. So we came up with the concept of application usability levels. This is led by Alexa Halford and lots of other people from this team. And it really helps define the phases you go through. So say you have a piece of code that does some cool science, and then you go to a conference and you talk to a forecaster and they say, this is really cool, I'd love to use this as a forecasting tool. What do you do to get from that point where you use a cool code on GitHub to something that an actual forecaster can use? So you go through different phases that we've now defined, where you start off with your research project, you then develop it and you test it, you verify it and validate it, and then actually take it through into operations. And we've defined various different levels that we hope will help people in the research community understand this sorts of transition process in a little bit more detail, and help them also kind of, I guess, communicate with the user community, whether these users are other scientists or forecasters, or even the end users like spacecraft operators or power grid companies, or the insurance industry. So these different levels will have now international guidelines associated with it. So for example, if you're talking about validation for a particular software project in space weather, we can start defining international benchmarks and performance metrics that these sorts of things should be compared against. Or if you're talking about the testing, you'd have special guidelines for the code that you use and the templates you use. So I'm not going to go through all the levels, but if you're interested in this at all, and in general just taking a research project and transitioning into something that's more kind of, I guess, applied, come and find me and we can chat about it a little bit more in detail. Thanks very much.
Thank you, Sophie.
Okay. So I am Abby. I am one of the lead developers of Stingray, which is an open source spectral timing software package. I am listed here. There's also Matteo, Paul Baum, Daniela Huppenkoten, and Simone Migliari are the other leads of this, and we have many other contributors as well. And my contact information is down here, and that's the Stingray website. So why do we make Stingray? So there is not much public X-ray timing code. There is like private code that your supervisor wrote and the code that you had to write, and code of like this research group and that research group, where if you're like on good terms with them, they'll like maybe send you a tarball. So it's mostly like legacy code, and it's all a black box. And it's also not written in languages that most students these days know. Like most of it's Fortran 77, Fortran 90 if you're lucky, which is fine, but not many students are easily able to use that. There's also no public X-ray spectral timing code, so this is looking at spectral variability on very rapid timescales, because this is a very new field, where we are defining public code here as anybody can read the source code and the code is well documented. So we created Stingray, Hendrix, and Dave, where Stingray is kind of like the library of tools. I had to spell out application programming interface when I presented this at the AAS head meeting because they didn't know what that was. So this is the tools and also the tutorials in the Jupyter notebooks. Hendrix, built on top of that, is the shell script interface. This comes from Matteo Bacchetti's Malt Pint tools for Newstar. And then Dave is a graphical user interface that Simone and Paul work on that is commissioned by ESA to be a GUI top for Stingray. In Stingray, this is what I work on. This is a library of time series analysis methods. So we have power spectra, cross spectra, bispectra, lags, RMS and covariance, coherence, cross correlation, GTIs, pulsars, and QPO searches. It also has a simulator and modeling. It does all the things. This is what X-ray timing and spectral timing people want. We talked with them at a Lorentz Center workshop, and we have done our best to include pretty much all of this at this point, which is great. Coming soon is going to be phase resolved spectroscopy for quasi-periodic oscillations. This is a plot from my PhD thesis, and we got a Google Summer of Code student, Swapnil Sharma, who is going to be working on this with me and Matteo. So this particular tool and technique will be added to the Stingray library toolbox very soon, by the end of the summer, which is very exciting. So in summary, X-ray spectral timing is joining the ecosystem of open source Python software. We are an AstroPy affiliate package. You can pip install Stingray or fork it on GitHub. Our code is github.com/Stingray software. The tutorials are github.com/Stingray software/notebooks. And there is a notebook tutorial for every single one of our tools so far. Some of them are very basic tutorials, but this is to help teach students and also kind of show people who are very experienced in the techniques, but not in Python, how we are doing it. And also, one of the things I was pointing out is that software is vital for the future of astronomy, but you all know that. Yeah, thank you. I have 1:38, so I can take a question. Me, thank you for asking. The name Stingray comes from conference-induced overcaffeination sleep deprivation, where if you take a stingray and lay it on its side and take an X-ray of it, then the top bit, the top half, looks like the power spectrum of an accreting black hole in what we call the low hard state, where you can see the broadband noise from the accretion disk fluctuations. And we got very excited about this, and so then I made the logo to reflect that to make it slightly less confusing for X-ray astronomers. Yes. Ask Daniela. Yeah. Yeah, no, it looks cool. It was a name. We wanted Ray in the name, and yeah, this is what we came up with. Okay, I'm actually done now. Thank you.
I'm disappointed you didn't have the clip this year.
I did know.
So the code for my lightning talk wasn't actually completely written. I was trying to debug it today, and I came up very short on time, but in one of those fortunate bits of luck, we had an unexpected visitor today. James Powell is the vice president of NumFocus. NumFocus provided support for this conference and plays a crucial role in underwriting and helping to manage several packages. You're all familiar with NumPy or SciPy, so I'm going to give a few of my minutes to James to say hello, and he'll be back on Thursday, I believe, too. And he's got a bag of goodies.
So hi, everyone. I'm James. It's a pleasure to be here. I come here bearing stickers. I've got a lot of them. I've got AstroPy, YT, SumPy. I've got a lot of stickers in here. Matplotlib, we made sure to get enough for 150 people. So you're going to be able to cover everything that you own with as many stickers as can fit. If, in exchange for those stickers, I could just bend your ear for 45 seconds to just tell you very briefly what NumFocus is all about. Many of you may not know how NumFocus started. It was originally formed by the core developers of IPython, NumPy, and Matplotlib as an entity through which they could raise money. When NumPy gets a large grant, they need a bank account, they need an entity. And beyond just its 501c3 nonprofit status, NumFocus has really evolved in something much greater than that. NumFocus right now is focused very keenly on ensuring sustainability of open source scientific computing software. And my role with the NumFocus is about figuring out how to make this organization a little stickier. Because in my reasoning, it's not enough for an organization like NumFocus to be able to succeed, because when Stan brings money in, Columbia takes 60 cents out of the dollar and NumFocus takes 20 cents out of the dollar. We need to really focus on how we can take all of the projects that are supported by NumFocus and build a true community behind them, solve common problems across all of the projects, bring the different communities together. For example, some of you in the audience I've seen at other events, some of you I've never seen at events. And so we need to figure out how we can build an integrated community that benefits all of the projects under the NumFocus banner, including YT, AstroPy, what else? SumPy, JOS, Open Journals, Jupyter. Were there anything else that was talked about at this conference that's a NumFocus project? And the carpentries as well. So that's what NumFocus is all about. I'll hand it over to Matt, and I'll be around for the rest of the day today and maybe on Thursday. So if you have any thoughts or ideas of what we can do at NumFocus to better support your community, please let me know. Thank you. I hope I didn't take too much of your time.
No, you're fine. You're fine. Oh, perfect. Okay, so I'm going to show you a couple of Jupyter widget things. So Jupyter widgets are there's a package called iPyWidgets that lets you put interactive controls into a notebook. Over the last year, there's been, I would say, a lot of work done in making higher level widgets. So initially it was just drop-down boxes and checkboxes and that kind of thing. A couple quick examples. This is a package I wrote called Reducer that comes with a browser. So you feed it a directory of fits images. You tell it how you want that information organized. So I've got it organized by image type and exposure, but I could organize by object or filter. You click on an image and it displays, and you can look at the header. I put this together originally because I work with undergraduates, and I wanted them to be able to use a browser-like interface. So rather than having them write code, I put together a set of widgets where they could specify which image reduction steps they wanted, combine images in several different ways. There's some bounds checking. Oh, whoops. See how it's orange on top? That's because my low threshold was higher than my high threshold. Whoop, but now it's happy, and in principle I can let it go. What I've been working on lately is so there's a package that exists only on my laptop called iPyFits. I don't know that it will ever get out into the wild as something called iPyFits. Under the hood, it's using the AstroPy affiliated package Ginga to do most of the hard work, but it gives you, in just a couple of steps, a way to display a fits image in the browser, and you can zoom in, you can pan around. And since I've got 10 seconds left, if you have any idea what's going on with my PSF, please help, because it shouldn't look like that, and it's different all across the chip. So with that, I'll wrap up. And let's thank James and NumFocus again. Serious about the PSF part. I need help.
Difficult, but so let me start with a Python package that I've been writing for 5 years now, and it's for image and data processing for direct imaging of exoplanets. So I was inspired by all this, all the Python scientific software stack, and I emulated all the good practices, let's say. So it's on GitHub, available on PyPy, Python 2.3 compatibility, Sphinx documentation. Now it has several contributors. It has quite a few citations, and I would say around 40 users. So it's very niche in the high contrast imaging and image processing for exoplanet detection and characterization, exoplanets and extrasolar disks. So it has Travis CI, PyTest is a work in progress. We have low coverage. And so I would like to propose it as an affiliated package during this week. So here a little bit about the problem itself of how a sequence of images where I injected a very bright fake companion. It's there moving due to the observing technique. We're observing in pupil tracking mode. So the thing is that this is a really hard problem. You see the noise, and it's a needle in a haystack problem, and we have observed directly 12 out of 3,700 confirmed candidates. So it's a really hard problem. So in VMP, we can, from a single dataset, have different views, thanks to the fact that I implemented a bunch of algorithms that have been proposed the last 13 years, plus a few of my own. Then there are Jupyter tutorials are in that place, and sure, reproducibility, yay. And this is something I started to work on 1 month ago at EWAS, and it's a high-level API. So it's so as it was, and as most people is using the package, it's a large collections of algorithms, of functions. And now I created this OOP API to just glue everything, and I think it's really cool, and users will definitely like it, and yeah, there's all stuff you can do with it. Now, second thing, how to frame this astronomical problem in a machine learning framework, right? And yeah, coming back to what I was saying, summarizing the machine learning conference. So this is machine learning in a nutshell. Then you have one learning framework where you have unsupervised learning, so you don't have any labels, and you can have different type of problems, clustering, dimensionality reduction, low-rank modeling, density estimation. Then if you have labels, whether they are classes or just a variable, then you may have regressions, classifications, or you can have reinforcement learning. In my problems, I framed my signal detection problem as a binary classification supervised learning problem. And here is, yeah, just optimization terminology on how we learn a model of parameters theta from a labeled dataset. So basically you have samples. In this case, you have muffin and Chihuahua, or Chihuahua muffin, I don't remember anymore. So you have that, and then you have a network architecture. It's how the weights are assembled. And you have a loss function, which is a measure of error between the original labels and the prediction of your function, plus some regularization of the parameters to avoid overfitting. And then, yeah, you optimize that with some sort of stochastic gradient descent. The cool thing about this is that there are these existing frameworks which are developed by multimillionaire companies, and they are open source. So you just have to go there and learn how to frame your problem and play Legos, basically. And then you can train these really complex models and do cool things like this. So framing the whole problem that I was describing before as a machine learning problem, and have binary maps at the end, and really improve the sensitivity to really faint companions. And this is, of course, possible by not reinventing the wheel, right? So, but by relying on the Python scientific stack and well, TensorFlow and the package that I developed myself. So thanks.
Hello? Okay, so I'm gonna one up whoever did the live demo, and I'm gonna do a dive demo on a Windows laptop, Windows 7, with one hand. So we'll see. See who can top this tomorrow. Okay, so I'm not gonna explain all the code because I only have 5 minutes, but I'm gonna explain in short. Mostly Synfort, but also a bit of PySynfort. So if you have used Synfort in IRAF, it's basically a Python replacement. And it's also the next generation of PySynfot, but I cannot name it PySynfot because it's going to be too confusing. So I just take the Py off. So first of all, there's some Python 2 compatibility stuff. And then I'm going to try to plot Vega. So this basically what it does in the background by default is it downloads Vega from one of our data servers. But here I'm using from file, a local file, because I don't trust the internet connection. And then I say, well, I also want to convolve it with a Johnson's V filter. And then I'm going to normalize the Vega to 22 STMAC in the V band. Oh, sorry. I'm actually normalizing it, not not convolving. So this is Vega normalized to what I just told it to normalize to, and here is Ford lamp versus wavelength in angstrom. So if you want to model spectra, this might be of interest to you. It underneath everything, it uses AstroPy modeling, and it understands the AstroPy units. So you can also plot it with different units and with different limits. One hand demo is not very easy. So here I zoom in into a feature of interest. If don't ask me what line it is, I'm a coder, not a researcher anymore. So here it is. A line shows you across angstrom in F lamp now instead of Ford lamp. So now I want to create a box band pass. So I use the box 1D model from AstroPy, gave it a central wavelength and a width, and I'm gonna plot. So now I have a boxy throughput there. And next step is I want to create an observation with this box throughput and my normalized Vega. So I pass them into the observation object and plot. So now so now for the demo purpose, the throughput is designed to central around the feature. I just show you, of course, in real life, it's not gonna be this ideal. But for demo, it's all nice and peachy. So you see now your observation only has that feature of interest and very high signal to noise. So I want to see the count rate. So here you pass in the area of your telescope. Usually is the area of your primary mirror. I think, yeah, the default here is the HST, size of HST. So here's my count rate. Of course, you can do all this in PySynfot too, but here it also gives you unit and you can pass in AstroPy models. So this part, I'm just gonna show you I can fit the absorption line, but I'm not gonna explain in detail what it's doing. It's using AstroPy fitter, and it gives you the best fit. The trick with this though is you have to give it a decent initial estimate or the fit might be way off. So I'm gonna plot. Oh no, running out of time. All right, so plotting it, the fitted shape and center, very nice. And now I'm gonna calculate the equivalent width. So there it is, 26 angstrom. And in the last 10 seconds, I'm gonna show you ST-Synfot. This one is you need to download a bit more data, and I didn't download all of them, so hence the warnings. Run. There, ACS bandpass.
Thank you very much. That was a commendably successful live coding demo.
Awesome. So I am here to talk to you about the data carpentry curriculum for astronomy. I'm here on behalf of myself, Phil Rosenfield, and Rodolfo Montez. And we have put in a proposal to develop an astronomy curriculum for data carpentry. I've been running the software carpentry workshops at the AAS for I think the last 4 years, and I've been doing software carpentry workshops for the last 6 years. And this would be a 2-day workshop that would be considered the next step after a software carpentry workshop. So there we teach you Git, GitHub, Python, bash scripting, and then we've thrown in different things, most recently an intro to SQL. And so this would be the next thing that you do, looking at data management and data visualization. And the idea is that we would develop it for astronomy, but we would develop it with broader goals in mind, that it should be easily extensible to other AIP, American Institute of Physics member organizations. So maybe if you do acoustics, you could do this, or if you're doing some kind of physics that's not astronomy related, you could hook in lessons to the lessons that we are making. And we actually have a grant that is funding some of this development, and hopefully we'll go into paying someone to do the development. So the curriculum, as we've outlined it so far, and this is kind of hot off the press, we've been talking about this over the last month, we brainstormed at the AAS in January, is to have a unit on data management and longevity. And this would be looking at how do you read data, how do you clean it, how do you write it, and then how do you scale that writing depending on how much data you have. And doing this in a way that's helpful to future you and future group and maybe random users, hopefully at some point. We've thought about doing this with pandas. We've also considered AstroPy tables. If you have strong feelings on any of this, let me know. We are working on defining the tools in addition to defining what the lesson goals are. So the next piece, and this is the big piece, would be multidimensional interactive data visualization. So this is looking towards having this higher dimensional data and what is the best way to interact with it. And we want to set students up to explore and visualize multidimensional data sets, and then extend that to how do I create reusable code for my data visualization. And we're thinking this might be a place where we throw in classes kind of as data containers that can maybe have some advanced plotting techniques on top of them. We have initially been thinking about using Bokeh. We also know that Pandas has some plotting capabilities. Maybe we can combine them. None of us knew about Altair, but it's making its way around Twitter. And so if this is something you have experience with and you'd like to advocate for that, I would be happy to listen. And then the final step would be actually publishing your data. So the AAS journals are now accepting Bokeh plots. That was a reason that we were leaning in that direction. So the ability to actually publish an interactive plot that people could select what their axes were and maybe look at the different dimensions of your data. And then also looking at self-publishing, possibly spinning up like a Heroku instance or something where you could put your data on your website, people could interact with it. And then out of this, talking about the longevity of your data, producing a DOI, possibly an intro to Zenodo or something like that. So our timeline this is based on the data carpentry lesson incubation. We are in the process of outlining the lessons right now. The next step is to develop them. We do have some funding for this, and we are looking for a developer. If this is something you think you have some free time, we don't have huge amounts of funding, so like maybe graduate student level funding. But if you also have time where you're like, I would like to give back to the community, this could be part of my outreach, this is something I'm really interested in doing anyways, and we could combine institutional funds with these funds, I'm interested in talking to you. We will then put this out for community feedback. We will incorporate that feedback. We'll do a test run on potential instructors and developers. We'll have a hackathon to finish the lessons. Then we'll do a formal workshop, maybe at January 2020 AAS, and then ultimately the lessons will be hosted on data carpentry. So if you would like to help give us information, this is a mailing list, and when we solicit feedback on the developed lessons, that'll be there, and that's my email. So this is in the document, you can click to it.
Thank you very much.
Okay, sorry, I don't know macOS, so I just wanted to show you some nice pictures of the Hubble Ultra Deep Field. And here, it's not the HST picture, it's the Muse VLT1. Yep. So it's a 3x3 arc minute field with 900 pixels on each side. And the difference with HST is that for each pixel, we have a spectra. So Muse is an integral field spectrograph. We have a resolution of 0.2 arcseconds, so a bit worse than HST, of course. But thanks to having many spectra, we could find some 1,600 redshift on this field, so 10 times more than previously. And it was also possible to find, for example, 72 Lyman alpha emitters, which were not found before in the HST, which is a very deep image. So there are many details on the paper. The main point for me here was to mention that Python is used almost everywhere here. The data reduction pipeline is in C from ISO, of course, but then almost everything around it is in Python. The reduction workflows, all the analysis, we have sky subtraction, an additional sky subtraction, which is in Python and publicly available. All the data analysis, source detection, spectra extraction, and redshift estimation also. A big part of it is in the MPDAF package, which is available. And we expect, of course, to put more tools in the future. So just to show an MPDAF example, which is quite close to Spectral Cube or the new ND Cube. So we can read data cubes and extract spectrum, narrowband images, fit, do a lot of things with images, spectrum, and so on. And finally, we also have now nice lasers on the UT4. And so ground layer adaptive optics now for Muse, and soon also laser tomography adaptive optics. And I'm working on a PSF characterization with a PSF that varies with the wavelengths. And that's probably a good idea for the next days to do 3D fittings with AstroPy modeling. Thanks.
All right. I just wanted to point out one of the things that was talked about yesterday a little bit by Carl, which was publishing, sort of publishing on GitHub in some sense. So Nanograv in our last publication, big publication with our 11-year data release, was our stochastic analysis. And so one of the things we did was we just made a new repo on GitHub that had our stochastic analysis in it. So this has all of the data. So if I go into the 11-year data, go into these are our parameter and timing files. So this is the full ephemeris for the pulsars, along with all of the timing data that we would need to run all of these analyses. And in here is a bunch of models that we run. So this is just using the software that we use. It's called Enterprise to do all of our stuff. It looks a lot like PyMC3. And you can just surf around in here, but if you go to this analysis notebook, there is a Docker image that you can download, and once you have the Docker image downloaded, you can just run this notebook and go through, and this is exactly the analysis that we did and ran to get our results. Here are the chains from a Bayesian analysis run. Here is more chains. Here's the reason why we are publishing an upper limit and not a detection from that posterior. So everything is here. It's all on this Docker page. And so you can go through and run everything. the README here has all of the pertinent information. So this is where you can go to get the Docker image. Here's where you can download Docker. Here's the software that we've used. We use this software that's called Enterprise, which has all of the documentation in it. If you go to the tutorials, this is our 9-year analysis. You can download the notebook here to run the 9-year analysis if you want to. So it's all there and available to go do. So it's completely as transparent as we could possibly make it, right? So that's one of the things we've done. And then the other thing that we are working on is really trying to make this all based on Python. One of the reasons you need a Docker image is because there's a lot of legacy code for timing these pulsars. We still use Tempo, which is the legacy code that Joe Taylor timed the binary pulsar with, the Hulse-Taylor pulsar with, and we still use that to check our pulsar timing data. And so we've been working on a different package, which is called Pint, and Pint is a nested acronym. It means Pint is not Tempo 3. That's what it stands for. And this is almost all of the stuff under the hood in Pint is based on AstroPy so that it will have continuous support. Right now, Tempo is supported by one of Joe Taylor's graduate students who is now a senior faculty. And so we have another code that's called Tempo 2 as well, which is written in C++. So we have sort of 2 versions of the same code, and then Pint, which is completely separate. And one of the really neat things for Pint is that it has a lot more flexibility. And so besides having the same radio telescopes and observatories that you would normally have for pulsar timing, we have the ability to look at Fermi, gamma ray data, and the new nicer data, the new X-ray data to time pulsars as well. So this package has allowed us to do that kind of timing. And so the hope is the next time we do one of these, write one of these papers and put it on to GitHub, that we will be able to have everything that you need to be pip installable. So you could just pip install everything, run it from the data that's already here, and have a look at all of that. And we even used a, let's see, this is a GitHub webpage that has sort of a rundown of the paper, rundown of pulsar timing in general, and then of course links to stuff on the archive. So I just want to show an example of how we've been trying to make our analyses as transparent as possible, put all of our code online, and it's all there for you to see. So thanks very much.
Hello. So I just wanted to advertise the next Dot Astronomy conference, which will be taking place in Baltimore at the end of September. Hands up who's never heard of Dot Astronomy. Okay, not too many people. So Dot Astronomy, it's now the 10th year that we are hosting the conference. We always struggle with describing what it is, but this is a definition we've come up with, a gathering of people helping to build the future of astronomy at the intersection of tech, outreach, and research. So we have, we bring together a lot of people who build cool tools, who have worked on new methods, and that can be for their research, but it can also be for public engagement or for education. So it does share a lot of commonalities with a meeting like this. Which is why I thought it would be good to advertise. So for 2018, we have, so we'll be at the Space Telescope Science Institute, and the meeting will be chaired by myself and Arvin Smith. And the rest of the SOC, Eric Tollerud is also on the SOC. Steve Crawford was the lead organizer for Dot Astronomy 9 last autumn. So come talk to any of us if you do want more information. We've kind of identified some themes. So STSCI is a big center for space astronomy. So we'll have a bit of a space theme in our talks. And because it's also the 10th edition of Dot Astronomy, which is a bit of a milestone, we wanted to have this kind of bit of looking back, a bit of retrospective at the last 10 years. but also from a scientific point of view, kind of the past theme, kind of like what we do with data and archive and storage, and what we learn from our past, and then also really looking towards the future space missions that are coming online, but then also how archives, how data exploration is all going to evolve in the future. For those of you who've been to dot astronomy in the past, you know these themes are very loose, and we really just kind of want to invite a very wide range of interests and skills. The program is very open. It's very very similar to conferences like this. So we have a lot of unconferences. We have a full hack day, and we always start with a day 0, which is kind of for general introductions, and we do some tutorials to kind of make sure that people are set up for the rest of the conference. Yeah, so I think in astronomy, we were the first to do this kind of unconference format. I think we organized the first astro-themed hack days. So I do think, you know, the AAS hack days and everything are basically all organized by people who came to dot astronomy and liked that. So we're very proud of that. That's definitely one of the nice things to see. Just the confirmed invited speakers we have for so far. We might have 1 or 2 more by in the next few weeks. Andy Connolly, Sarah Hurst, Jarita Holbrook, and James Howison. These are all excellent top scientists that we're very excited to hear about. And it'll be a mix of a bit of you know, science and space and future missions, as well as also some more cultural, sociological talks. So just wanted to finish off with some more info. The pre-registration form is now up and open. So if you follow the link, this document is in on the Google Doc, by the way, and should be accessible. You can start filling in the pre-registration forms. We'll do a bigger plug and email announcements and things like that. But basically, we are ready to take your forms and come talk to me, Arvin, Eric, Steve, any of the other, Kelly, Emily, many of you have attended in the past, or just, you know, use email. Thank you.
So I'm one of the developers of SBPy, which is a package for small body astronomy. Oh, okay, sorry. So yes, I will talk about SBPy, about its current status and background about how it got started. So this is developed as a package to perform common tasks in the field of comet and asteroids astronomy. The current status is that there have been some efforts from several people to develop some of the tools that are listed here, like image analysis and spectroscopy, but some of those packages are not publicly available, and even those that are available are written in Fortran typically, and may not be released under an open source license. So we decided to start this project. I can show here the design of the package. The package was based on an online survey that was carried out about a year ago by Michael Momart and Mike Kelly, that was sent around in the comet and asteroid community to ask about potential tasks that should be included in the package and that are useful in general for the community. So here on the right there are the modules in the package that have science applications, like the spectroscopy analysis of line emission from cometary dust and cometary coma, and image enhancement of comet images. And on the left there are the support classes that we use for all the other modules, and also to query online services for minor body astronomy. Based on the results from this survey, Michael Momert put together a proposal to PDART. NASA PDART is planetary data analysis and restoration tools. And luckily the program was selected, and it got funded starting this month for a period of 3 years. And we have 3 co-Is that are experts in different aspects of minor body astronomy, and also a few collaborators that have that will provide their existing code. Sometimes this code is not in Python, but we will adapt it for including in SBPy. Also, as part of the PDART program, we will have funding for internet students at Goddard. We will have students over the next 3 years during the summer to work on some aspects of the code, and we will also set up tutorial sessions at DPS, which is the planetary meeting of the AAS meeting that is held every year, where we will teach how to use this package to the community. And also some of the things that we need will be implemented in other packages of the AstroPy ecosystem, such as the query different services that will be added to AstroQuery package, and also to the Ginga image viewer. We will release those as a plugin to Ginga, so those will be contributed to other packages of the AstroPy ecosystem. I think that's it.
Hello. Okay. So I'm going to give a short overview of my work. I work for SOAR telescope, and we are developing pipeline. Well, we have currently work only for spectroscopy, but it's also supposed to work for imaging. So here's a screenshot of the GitHub page. So in the team, I'm the writer, for if I can call it that way. Cesar is the chief. I mean, yeah, the boss. And Bruno also collaborates with the. He's very good with Python, and he's always looking at the details. So the motivation for building a pipeline is basically Goodman. The Goodman high throughput spectrograph is the most used instrument on SOAR, and uses the 65% of the time. And there was no tool available for the data reduction. Also, people, I mean, the users use their own tools. I don't know, IRAF or whatever. So we set these goals. It has to be easy to use. It has to be well documented. So I don't know. I would like some feedback if anyone can give some. We follow the standards for coding, so the code is possible to share, and there's also the possibility of me, I don't know, moving to some other job, and the observatory wants that my work is not lost if I leave. So that's why they told me this. Our focus was to use Python only, and if possible, only AstroPy tools. But of course, when we started, not everything was available. So what else? So it uses 2 scripts to reduce. So red CCD does the 2D corrections, and red spec does the target identification, extraction, and wavelength calibration. it works automatically. So more or less, I would say in less than 5 minutes, you can reduce full night. So the problems, we didn't plan it very well since the beginning. So I have had to rewrite the code a couple of times, which is usually healthy, but not when you haven't planned your code. So, but it's one of the things I've learned. Also, the Goodman spectrograph is is highly configurable, so it has many possible configurations. One other thing is that it has 2 cameras and the headers are different, so that was kind of complicated. For cosmic ray rejection, initially we started with LA Cosmic, but as far as I know, it's not designed to be used in spectroscopy. So we implemented DCR, which is written in C, and is implemented as a sub-process. So I think there's no. Oh yeah. So I have 30 seconds. So regarding the well-written solutions, this is how IRAF writes the linear solution, which is very simple to read. But for non-linear solutions, this is I don't know why it put this. Well, so this is the string that you have to interpret or to decode to be able to reconstruct the well-written solution. Well, you can see more of this example on the notebook, but I wrote some tools to be able to read the nonlinear solutions, and well, it works. So yeah, I think I don't have more time. Sorry.
Thank you. Right, yep, so that is all our lightning talks. I believe we have to be out by 6, is that correct, Matt? Yeah, sure.
There were 3 lightning talks that we didn't get to. Sorry. There are 3 lightning talks on the list that we didn't get to. I don't know when we're going to fit those in, but we will fit those 3 in sometime in the next 3 days. That shouldn't be a problem. So if your name is on that list, count on it.
Thank you, Matt. And let's thank all our speakers again.